Welcome, everybody. I realize it's a lovely day out, so good to come celebrate Pi Day with me. Everybody wear your Pi shirt? Yep. This is, of course, one of the most important days of the year, so I'm glad that you're not going to miss it. But before we get to Pi, which we will, I wanted to briefly recall what we were talking about last time, and I decided to make it real by showing you the full-blown x86 memory model with segmentation. And the things that I wanted to point out is, number one, the segment selector actually doesn't come from the address, it comes from the instruction. So what you see there is a move instruction using the GS segment. Okay, and that segment selector goes into a descriptor table to pull out the segment descriptor, okay, which gives you a base which is added to the offset, giving you a combined address, which is a linear 32-bit address in this instance. And now you're in 32-bit virtual address space, and that goes into a two-level page table with the 10, 10, 12 magic number divisions that we talked about, right? So 10 bits going to the first table, 10 bits to the second table. Intel likes to call the first one a directory and the second one a table. They're all just kind of tables in the same format. Each of these have to be contiguous sets of entries because this is an index into the entries. All right? Questions? So the one important thing to keep in mind is this up here. So this, there are actually bits in the instruction that select the segment, not out of the address. Okay. So the other thing is we started talking about caching to remind you guys of things. So here I've got two scenarios. One where the processor accesses DRAM right away. The other where the processor accesses through a cache and then DRAM. Which one is faster? Okay, I'm hearing the second one. Not necessarily. Depends on the workload. If you put a really bad workload against the second one, that's actually slower. Okay, now most of the time it's faster. But so we have something called average memory access time, which is hit rate times hit time plus miss rate times miss time, where, of course, hit rate plus miss rate is 1. And so as a good example, here we have 90% hit rate. We have 0.9 times the 10 nanoseconds, so we're evaluating the second one, plus 0.1 times, well, why do I have 110 here? 10 plus 100 is 110. Good. Why am I adding 10 and 100?
Because, like, miss time, you would have to take 10 nanoseconds for the second level cache, and then when you're in main memory, you get 100 nanoseconds for this.
Yeah, so typically what happens is this access level ends up part of your final access after you've gone to the trouble of going down and coming back up. If we actually have a higher hit rate, of course, the average memory access time is shorter. And I wanted to point out that this is all recursive. So the miss time, which we're using in that formula up there, is really the hit time plus the miss, what we call penalty, which is really the total average memory access time for everything at the second level and down. So you could have this be recursive. Okay, so rather than main memory DRAM, this could be a next level cache and so on. Okay? Good? And I apologize, by the way, the version that I had posted, I was going a final pass through my slides, and it actually didn't add hit time and miss penalty together. So there should be correct now. Yeah, go ahead. Good question. Can you hit this, go into the cache and then main memory at the same time and thereby get a little bit of improvement? Yes, and in fact, processors sometimes do that, especially when the second level cache is actually on the same chip as the processor, so you can issue things in parallel. The downside of that, though, is that if you've issued something to main memory and you don't need it, then you're actually wasting bandwidth at the next level. So that has some consequences. It's not always a good thing. All right? Good question, though. Okay. Are we good? Now, we also talked about how this memory hierarchy extends widely. So I actually had tape here to see if anybody even knew what tape was last time. But today what really happens is typically you've got many levels of cache on the chip. So multiple cores often share at the third level. And then you've got main memory, which is DRAM, which is then backed up by SSD, which is backed up by disk. And so, again, the whole point of this hierarchy is the speed of the thing at the far left, which is the registers, and the size of the thing at the far right, which is the disk in this case. Okay, that's what you're trying to do. Get something that looks like the speed of the thing on the left, but has the size of the thing on the right. And, of course, that's locality is the way we get that. All right? Good. Intel has a bunch of options now, and so do others. Like there's an Intel Optane, which is something not quite flash that's sort of closer to main memory, and there's some cool things coming out with nanotube things that are as fast as DRAM but non-volatile. So there's some cool things that are going to be added to this hierarchy very shortly. All right. So again, the 3 C's plus 1. Okay, remember compulsory misses are ones that happen because you've never seen it before. Capacity misses happen because you saw it, you put it in your cache, but it got kicked out because the cache was too small. You go to get it again, it's a miss. That's a capacity miss. A conflict miss. How do you know what a conflict miss is about? Anybody know how you figure out? So a conflict miss, first let's talk briefly about what it is, then we can figure out how to measure it. Conflict miss is, I've got a direct map cache. I load one address into memory, or into cache. I load another one that overlaps in the index bits and therefore kicks the first one out. I go try to read the first one again, it misses. That's a conflict miss because they conflicted. But how do you know if you've got a given miss, whether it's a conflict or a capacity miss? Anybody know? We have 61 CTAs in the front row, I'm assuming. Don't want to identify yourself as such at the moment? Yeah.
Like for a capacity, there's definitely like the idea like there's like no more room like in the entire cache.
Yeah.
That'll probably be like something like fully associated that can go anywhere.
Yeah.
And like once that fills up, then we know that no more could be added unless you have to kick something out.
You're kind of on the edge there of the way people usually think about this. What you do is you simulate it. That's about right. So you simulate a fully associative cache of the given size, and you look at all the misses. And then you go to a cache of limited associativity, like a 2-level set associative, and the additional misses are conflict misses rather than capacity ones, because the capacity ones got taken by the second level. All right, good. And then, of course, coherence misses are ones where I loaded it into this cache. This cache on this processor wrote it, so it kicked it out. I go to load it again. It's now a miss. That's a coherence miss. Okay, so those are the 3 plus 1, and I call it 3 plus 1 because Mark Hill in his original thesis only talked about the first 3, and the fourth one is usually added after the fact. Okay, good. Now, I also quickly reviewed this, so you all ought to be very familiar with what a direct map cache is. What we do is we take the index, which is some bits in the address that are above the byte select bits. So think of this as the offset in our page algorithms. This index picks exactly one item out of the cache, so this directly addresses that item. We check the tag. If it matches, we get a hit. If it doesn't match, we get a miss. And so we get conflicts in a direct map cache for all addresses that have the same 5 bits here. Okay? Now, we could turn that into a 2-way set associative that looks almost identical, but notice there's one less cache index bit here, and the reason is that I took my original cache, I split it in 2, and so this index now picks one of 2 sets, and so now I have 2 tags I can compare, and the one that matches, if it matches, is a hit, and I get data out. If they both miss, it's a miss, right? Okay. Which one is faster, the direct map or the 2-way set associative, and why? Okay, first answer ought to be wrong question, Kubi. What do you mean by faster? Go ahead. Okay, good. So your answer, the reason this is an ambiguous question, right? Your answer was, given the workload, I'll have less conflicts, the overall program time is faster. Good. What's a different answer to my question? For any given access, which one's faster? Yes?
The direct map would be faster because there's less comparison.
Yeah, so in the case of the actual single access, that's the second question, this one is slower because I have to do a comparison, and look, after I match, the data has to go through a mux, and so there's a couple extra levels in hardware. Okay, good. So whenever somebody asks you which one is faster, you ought to say, what do you mean? Okay, or what's your definition of faster? Okay? Fully associative is a great example of that. So in fully associative, there's no index. Every line has a tag that's compared against the cache tag. The one that matches because of an equal, then you get the byte out of that. Again, here there's zero conflicts. Okay, because we can put any addresses in here we want. Which one of these is faster? All together now, Kubi, what do you mean by faster? Okay, very good. If I mean by an individual access, this is going to be slower than all of them because these comparators take space, which spreads things out, which on a chip makes it slower. Okay, and you've got to do this actual equality and go through a bunch of muxes. And so this is going to be the slowest per cycle option, but it'll have far less conflicts than any of the other ones. Okay? And so it could mean that if you had a really high conflict scenario, you want fully associative because otherwise you're just replacing and conflicting in the cache all the time. Okay, there's your 61C for today. Actually, there's one other thing, I guess. So, of course, where does the block go? Direct map, there's exactly one place for it. Set associative, there's multiple. If it's two-way set associative, there's two places. Fully associative, it can go anywhere. All right. So I was just rushing through this at the very end of the lecture. So you could ask, when I have to kick something out, how do I choose the thing to kick out? Okay, so look. Back here on a two-way set associative, there's two places that we could put the data. Let's suppose the data that we're interested in isn't in there already. So that means that we're going to kick one of those lines out to put our data. That's what replacement means. How do we decide which one? Okay. What are some options? Well, random, flip a coin, or LRU. We could pick the one that's used least recently, okay, and that's the one that we want. Now, what's interesting, that might make sense, right? Pick the one that's used the longest ago. Except if you were in a hardware class, somebody might point out LRU takes extra bits. Okay? It turns out that there's a very cool circuit you can build that's a triangle, and so, it takes this kind of something of order square number of bits per line to do that, so it can be done. But if you were to also be in a hardware class, I don't know if they cover this in 61C or not, what you find is that random works pretty well for a lot of scenarios, especially when the cache gets really big. Random might not actually be too bad. And so going the trouble of doing LRU might not be worth the trouble in this instance. Okay, now when we get to paging, where, remember what I said at the beginning of the lecture, I talked about this miss penalty being all the time to get something when you miss in the cache. In a page fault, where we have to pull it off of disk, that miss penalty is 1 million instructions. Therefore, conflicts are bad, and maybe we do want LRU or something good, right? So random might actually be a good scenario for a hardware cache and a bad one for paging, and we'll get to that. Okay, everybody with me? Now, what happens on a write? So obviously we can write through. What's that mean? That means that every write goes into the cache and into the underlying DRAM. Okay, or write back where the data just goes into the cache and later we have to kick it out to the DRAM. Now, which one is faster for, what do you mean, Kubi? Which one is faster for paging if we're talking about a cache where the pages underneath are on the disk. Do you even want to do write-through? That sounds pretty bad, right? Because it means that every write the processor does then pushes the whole block out to the disk. That seems like if we're starting to think in terms of caching when we get into paging, write-through is going to be write-out, right? Kind of a bad idea, all right? Okay, pros and cons of each. So write-through, the pro is read misses never result in writes because the underlying thing's always up to date. The con is the processor waits on every write. Write back. The pro is repeated writes don't go to the DRAM, or in the case of paging, don't go to the disk. The con is it's more complex, and when you kick something out, you may have to write it back. Okay, this is all review for 61C. All right? Is this all ringing? You guys are vaguely ringing some bells here? Yep. Good. Good. So let's come back to our topic at hand here. So what if we want to apply caching to address translation? So we have a CPU on one side with virtual addresses, and we have physical memory on the other with physical addresses. And we had virtual addresses come in and physical addresses go out. So what do? Well, we build a big fuchsia-colored pentagonal thing we call a TLB, translation look-aside buffer. And the question is, we're going to use that as a cache, and we're going to say, is this virtual address translation cached? And if the answer is yes, then we get a really quick result. Then we don't have to go through the page table, okay? Otherwise, we got to do something by going to the MMU and translating, okay? All right? Pink, pentagonal, very important, okay? So, everybody with me? This is just applying caching to TLB. Most things in operating systems are caches in many cases. So notice also, of course, when we do the translation, because we've got to go through the page table, we save the result in the TLB, so the very next time we do that, we get a fast translation. Okay? The other thing that's almost always the case is there's always a write-around that the operating system gets where they don't translate. Okay? And that's so the operating system gets to see the raw data and do whatever it wants with it. Okay. So, question, if this works, is there any locality? Does locality in pages exist? How many people think there's some instances in which this translation cache will work well because there's locality? Anybody want to give me one or two of them? You can give me one. I would put you on the spot. Anybody have one? Yes.
You walk through an array that's on multiple pages.
You say again?
You walk through an array that spans multiple pages.
Well, if you walk through an array that spans multiple pages, the spanning part doesn't cache well, right? So why don't you start with you walk through an array that stays on one page for most of the time, and then it goes to another page. That would give us locality, right? What else? Okay, so you want to use the kernel, generalize that away from the kernel into what is it we're talking about? Probably instructions. Great. The instruction, the PC goes, and loops, right? So there's a lot of locality in instructions. Okay, so instruction accesses spend a lot of time on the same page. Stack accesses, definitely on the same page, right? Down, 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 up, up, down. You guys get the idea. Data accesses that have some page locality is good, but you can also blow out the TLB just by, for instance, doing an array walk that goes 4K at a time. You're guaranteed to touch a different page with every access, and you're going to blow out your TLB because everything's going to be a page fault, or it's going to be a page fault, TLB fault. Okay? And a page fault. All right. Can we have a TLB hierarchy? So the first slide, or second slide I showed you guys, had a cache, maybe multi-levels of cache, followed by DRAM. Could we do that with a TLB? Yes. Sure. Why not? In fact, there have been a bunch of processors that have something called TLB slices, where they put a little tiny direct map cache in front of a fully associative one. So that actually happens to get you faster cycle time. Okay. Everybody with me? So what actually happens on a TLB miss? I mentioned this last time a little bit. I thought I'd reiterate. So If we have a TLB miss, that means that we're trying to do a translation that's not in our cache. What do we do? Well, in a hardware traversed page table, the hardware in the MMU just looks at the current page table and does a walk through the different pointers in that page table. And eventually it ends up with a page table entry. And if it's valid, or in Intel, what is valid? Present, yes. The hardware takes the PTE, puts it in the TLB, and the processor continues without ever knowing the difference. Okay? If it's marked as invalid, it also puts the page table entry into the TLB, but at that point, it triggers a page fault, and now the operating system has to figure out what to do because the page translation is not valid in the page table. Okay? So let me say that again. So we have a TLB miss. That's just a cache miss. We walk the page table. We get a page table entry. That page table entry is either present or not present. Present, we just put the page table entry into the TLB and continue as if nothing ever happened. Not present, we put it in the TLB and take a trap to the operating system for a page fault. And at that point, the operating system has to do paging of some sort, which we're going to get to toward the end of the lecture. Okay? Now, contrast that with the software traversed page tables, which were made somewhat famous by MIPS initially. And what happens there is when the TLB misses, we do not have an MMU. We instead cause a TLB fault, which goes into the kernel and walks the page table in software. Okay, and then if it finds a valid PTE, it fills the TLB and returns from the fault. Otherwise, it's marked as invalid, and you're already in the kernel, so at that point you just call the page fault handler in the kernel, and the page fault handler takes over and does something. So notice the difference here is in the first one, the processor may never get invoked if the page table is valid if the page table entry is valid in the page table. The second one, the processor gets invoked on every TLB miss. Which one's faster? Depends on what you're asking, Kubi, right? So if you think about it, if there's lots of TLB locality, that second one's not too bad because you don't invoke it very often, right? This represents a TLB fault, in that case, represents a cache miss. And if you're not missing too often, then you're good. Okay? If you're missing a lot, that second one's going to be very expensive. Okay. Most chipsets give you hardware traversal these days. Okay? And the reason is, as you look at more and more interesting operating systems, they often have lots of address spaces, many different pages are translated in different ways, and so in potential there's a lot of TLB misses because they're doing sophisticated stuff, and therefore the hardware traversal makes it faster. Okay? All right, questions? Good. So, Happy Pi Day. So I thought it important, given that today is this most important and revered day, to say a little bit about pi. So one thing that's important to know, I think, is that 40 digits of pi are enough to compute the circumference of the visible universe to an atomic accuracy of a proton. Okay, so 40 digits are probably all the digits of pi you will ever possibly need. Okay, but pi is not about need, right? Pi is about want. Okay? So the best formula for pi is from Ramanujan, who had, I don't know if you've heard about this mathematician, but he had this amazing direct line to the universe. Nobody's quite sure where he got his answers from, but here is one of the best. That's not a minus 1 over pi, by the way. That's a dash, and it's 1 over pi is equal to this thing that came from his brain, and apparently every term that you add adds another 8 digits. And Google announced today, clearly because it's the most revered of days, that one of their employees had just calculated pi to, are you ready for this? 31,415,926,537,897 digits. You guys caught all this, right? 3.141592653. By the way, this is a real thing. You guys can find the announcement if you look it up. Now, you might ask why. And once again, remember, pi is not about need. Pi is about want. And everybody wants 31 trillion digits. This is, as far as I know, this is a new record. Yes? Huh? You know, E is the most underappreciated of numbers. Somehow it just doesn't get the enamored devotion that pi does. I can't really explain it, but such it is. All right. So happy Pi Day, everybody. And by the way, on this very same NASA link, you'll find out that NASA really only uses 15 digits in its most accurate of any calculations it does. So again, it's not about need. All right. I could say any questions, but I'm not sure there's anything to ask about this. Yeah, go ahead. Okay, fine. You know, I used to know a couple hundred digits. I think I'm down to like 120 or something. So, you know, you get older and the digits sort of disappear into the universe. I do know enough digits. I wrote this one down from memory, so that's easy. Oh, come on, guys. 3.14, 15926535897932384626433832795 288419716939937510582099744 59230781640628620899 and so on. You all caught my Pi Day t-shirt too, right? All right. So, back to reality. Project 1 peer evaluations are up. It's very important to fill these out, honestly, because they can impact your grade. We use the peer evaluations in combination with your TA's understanding of how your group is doing. And we have a few groups where there are some people not contributing, and TAs know this. And ultimately, it could be a zero-sum game where if you're really doing nothing, your points could sort of find their way out of the universe into your partners. So this is supposed to be collaborative design on your project, so please collaborate. And if you're having problems in your groups, let your TA know, let me know. Let's see if we can talk it through, because that's very important, all right? Very important that everybody works together. Okay. Otherwise, you lose digits of pi to the universe. Not a good thing. Okay. So very important. Do your peer evaluations, please. Project 2 is released today on this most important of days. Midterm 2 is coming up after the spring break, which is unfortunately advancing pretty rapidly. We will actually have a midterm review in the week after spring break, but before the midterm, to help you through, because we know that on spring break, again, digits of pi disappear to the universe. Okay, any questions? Yes? Do I know what? Oh, that's a good question. I don't know. Well, you know, the thing is that 31 trillion is not the last digit of pi, which we all know is 5. So I don't know if she hasn't gotten there yet. So, all right. So let's talk a little bit about exceptions. Okay. So we talked about exceptions a couple of weeks ago, where we sort of talked about things like divide by zero exceptions. We talked about system calls. We talked about interrupts. These are all exceptions. And the interesting question is, how does the state of the program get impacted when an exception occurs? So, for instance, here we have a user program's coming along, and in a processor without hardware table walk, suppose there's a TLB pop into the OS to do a software loading of the TLB, and then we pop back up. What happens? Okay, could we just skip the faulting instruction and go on to the next thing? Well, no, right? Why not? Well, because that load or store failed, because it didn't occur. Okay, and so what we have to do is we have to be able to restore back to the load or store that caused the original fault. Okay, and hardware, that's 152 or 61C, etc., has to help out by saving something, right? It has to tell us what the faulting instruction was, partial state of the pipeline, all the stuff we need to restart back here again after we've cleaned up the page table and the TLB. Okay? So, so that the fault happened, we clean everything up. When we start executing it again, the fault doesn't happen the second time and the program keeps going as if nothing happened. That's our goal. All right? And it's kind of an interesting question. Is a single program counter of the faulting instruction enough to do this restore? That might be a question. Okay? Because there's a program counter that points at the instruction that faulted. Is that all we need to know? And the answer is, depends. So we also need to save processor state. Save and restore registers, stack, etc. Okay? Especially if you're doing a software TLB. Imagine that you pop into the software TLB and you mess up all the registers and then you pop back up again. That's clearly not going to work. Now, in previous iterations of this class, we actually had MIPS processor that you were working with, and you had to write a software TLB fault handler. That was one of the labs or projects. Now, since we're using an x86 model, you don't. Okay, but the same thing applies here. Suppose this faulting instruction actually causes a page fault, and the operating system does something. We still need to restore. So this is still true about page faults as well. Okay? And again, this is not complicated. The green thing is the user program. The blue is the operating system. Whenever you pop in because of a page fault or TLB fault, you got to be able to pop out and continue where you left off without screwing up the user program. That's the bottom line. Okay? Question? Now, consider some weird things that might happen. So, what if the instruction is in the middle of something and then you get the page fault? Now what? Well, that gets messy very quickly. Okay, like for instance, you might have to unwind the side effects of the instruction. Take the stuff that partially happened, undo it so that you can restart it. Okay, or you finish off the side effects. So it got half done, you fix the page fault, and then you complete it. This is getting messy. This kind of question is something the operating system has to worry about because it's restarting after a page fault. Okay? And for example, here's an example of an instruction. Move stack pointer plus. It's incrementing the stack pointer and put a 10 in there. What if a page fault occurs when you write to the stack pointer? You might ask the question, well, did SP get incremented already? Because notice that instruction there both increments the stack pointer and stores. So what if we increment the stack pointer first and then store, get a page fault? We can't restart that instruction because then we'll get a double increment. Okay, is everybody starting to see the weirdness here? This is a little weirder than I'm sure you've thought of. For instance, here, a string copy from one address to another. Okay, there's a lot of what are often called CISC processors like the IBM, the S370, VAX, etc. What do you do there? Because you're halfway through the string copy and a page fault occurs. You can't restart the string copy at the beginning. So some cases what the hardware actually did was ran it twice, once to make sure everything was paged in and the second time to do it. Okay? That gets complicated. What about RISC processors? So here's my favorite. How many people remember delayed branches? They talk about that in 61C? Sorta. So the idea here is this branch is going somewhere and the delay slot immediately after the branch executes because of the pipeline. Imagine for a moment, you're branching somewhere, the load gets a page fault. How do you restart this? Because if I go back to that load and restart, I won't branch because I'm in the delay slot. So in fact, on RISC processors, there's actually two PCs involved in a fault. There's something called PC and the NPC. Okay, so that we can restart in a way that will restart that load and then branch to somewhere. And we need two program counters to make that work. All right? Questions? Or delayed exceptions. This one is my favorite to think about. I don't know if they talk about this at all in 61C, but here's a divide. Are divides fast or slow? Slow. Oh, you didn't even ask Kubi, what do you mean? Yeah. So a divide is slow, usually relative to something else. So you've got a divide, and it's taking a long time, and the load comes around and causes a page fault. But just before you get in the kernel, or as you get into the kernel, the divide divides by 0. Yeah, oops. Now what? How do you restart this? Okay, because you need to restart somehow on the divide after fixing up the 0, but the load also faulted, and now the pipeline is really confused, as is the programmer, right? What the heck? I don't know. So if you had your ideal druthers as operating systems people, where would you like the fault to point to, the divide or the load? Divide, right? Because the divide is the first thing the programmer thinks hasn't completed yet. Okay? Good. This that we're talking about are things that operating systems people have to worry about. Fortunately, there's something called precise exceptions. I don't know that they cover these in 61C, but I thought I would tell you about this. So what's a precise exception? It says that the state of the machine is preserved as if the program executes up to the offending instruction. All previous instructions have completed, and nothing afterwards has started. Okay, so in this scenario, the reason this divide and load thing is complicated is because a modern pipeline does them out of order, starts the divide and then starts the load and then figures out later that the divide screwed up. The point is, it doesn't matter what the pipeline does. When all is said and done and the operating system takes control, if there's a precise state, the operating system's only told about the divide, no matter which one fails first. That's a precise state. Because if the divide is the precise exception state, everything before is done, nothing after has started. None of the registers are altered or anything, and that's the good point for the operating system to enter. Okay? Now, there are some cases where you have sort of semi-precise, where things like mathematical operations are not precise. But certainly, things you need to restart, like page faults, better be precise exceptions. And they are. So when a page fault happens, you get the address of the offending instruction, and you can restart right there because you've got a precise state. Everything before has completed, that instruction, nothing after has started, and you're good to go. And so the only thing the operating system has to worry about is cleaning up that fault and then restarting back at the point at which the fault occurred. Okay? There is, by the way, there's a famous, depends on what circles you run, processor. The 88,000 was a processor that was used in a bunch of embedded applications like laser printers. And it did not have precise exceptions. In fact, it had a very complicated pipeline. And when you got an exception into the kernel had to figure out all the state in the pipeline, save it somewhere, finish the exception, and then figure out how to restart pieces of the pipeline to get it going again. It was a mess. Okay? And needless to say, people don't do that anymore, because there's enough transistors not to worry about it. So imprecise is surprisingly not precise, right? Performance goals often lead designers to give up on preciseness, but fortunately, modern processors pretty much all have reorder buffers and branch prediction, and in order to restart at a clean spot after something like a branch prediction or whatever, the reorder buffer fixes it, and it effectively lets you unwind things that happened before. And so if you've got branch prediction and reorder buffers, everything's precise. And it's really easy, and the operating system says, yay! Because you've got a single PC that tells you where things accepted. Where was the exception point? Everything before has completed. That instruction and nothing after has started. And it's a nice, clean state. And that's thanks to a bunch of things that handle out-of-order execution and branch prediction and all that stuff. Which, of course, are all the things that caused Spectre and Meltdown in the year of the 2018, namely last year. But anyway, Okay, precise exceptions. Any questions? So if you're writing exception handlers, your first question probably would be, gee, is it a precise state? Now, fortunately, today, the answer is probably yes. And especially in x86, the answer is going to be yes. You're good to go with your labs that you're working on, your projects. Okay. Good? So what happens on a context switch? So remember how we asked this question a lot of times last time. What happens on a context switch? You switch out the page table pointer, or you switch out the segment state. Now that we've got a TLB, we got to do something also. Like, well, TLBs map virtual addresses to physical addresses, and so if you go from process A to process B, process A and B think they have the same virtual address space, right? It starts at 0, it goes to 2 to the 32nd minus 1. If your TLB is caching translations and you just switch to a new process, then all of a sudden that process gets to use the translations cached in the TLB from the previous process. That sounds like an oops, right? Think about that. You switch out the page table, but there's still some translations cached in the TLB, and if you just switch from process A to process B, suddenly process B is using the translations from process A, and you've got a mess. Okay? So what do we do? What's the simplest thing? Yeah? Yep. Got to flush the TLB. So that's the simplest thing. If when you switch from process A to process B and the address space is changing, you could flush out the TLB. Now, of course, that becomes overhead because if I go back and forth between A and B too rapidly, I'm running a little bit, flush the TLB, running a little bit, flush the TLB, back and forth. That's a problem. Does anybody have any idea what else we could do? Yes. Yeah. So what really happens and this is not, this is only recently starting to show up everywhere, but you can actually put a label of what the process ID is in the TLB. And when you're in process B and you go to match the TLB, you will ignore entries from process A without having to flush, okay? And there's a lot of modern processors that are like that. So we can either flush the TLB or put a process ID in the TLB. Those are both options. This one down here is a little more recent in terms of showing up everywhere. What if the translation table changes? So what if you go to change the page table by putting something in? Oops, you better invalidate the TLB entry because that's wrong. So this is unlike a hardware cache because it's a cache on something handled in software. And if the operating system goes and changes the page table, it could be that the TLB entries are wrong. Okay, and at that point, you got to flush the TLB because the operating system's altered things. Okay? Questions? It's called TLB consistency, by the way. Okay. Before I move on to that, see if there are any questions on this. Think about that for a moment. It's a little bit tricky. Because the TLB is a cache, but it's not totally transparent because the operating system knows that it exists. And so there are ways that the operating system can alter the thing that's being cached and means that what's in the TLB is wrong. And you've got to sometimes flush it out just to make it right. Yes? No, you're throwing it away. Just throwing it away. So that, let me give you a good example of this. Process A is running, and we decide that we get a page fault, and we load a page into memory, and we update the page table. If we return and try to rerun the instruction, what happens? Well, we immediately page fault again because the TLB says it's a page fault, but the page table is correct. Okay, so what we have to do is flush the TLB so that when we go and try it again, the TLB misses, we go to the page table, we get the new updated translation, and everything works. Okay, and that's because the operating system can alter the underlying page table without the TLB changing under some circumstances. Okay, good. So we'll talk about one more topic, then we'll take a break. So what TLB organization makes sense here? Okay, so it's got to be really fast. Why? Well, because if you look, the CPU is accessing the cache through the TLB. Okay, why do we have a cache? Well, because memory is slow. So if the TLB is slow, then we've just slowed everything down. Even though we have a fast cache, if our TLB is slow, we have a problem. So it's in the critical path. And this seems to argue for direct mapped TLB to make it really fast. Okay, which is faster? Do you mean, Kubi? Direct access for a single cycle is faster for a direct mapped or lowest associativity. However, you don't want conflicts, because every time you've got a conflict, you've got to walk the page table. So that kind of argues that the conflict might be very expensive, and we want to have higher associativity. And furthermore, we could end up in a thrashing scenario with continuous conflicts between accesses, and then what? So we would like our TLB to never have conflicts, which says what kind of a cache is the TLB? Fully associative, yes. Okay? And you can go through a lot of scenarios. You can say, well, I've got a load instruction that's loading from here, and there's a store next to it, and I need, you would come up with how many TLBs you need per instruction, and you rapidly say, I need at least 3-way set associative, but in fact, people mostly do fully associative. So, fully associative. How big does it have to be? Well, it's usually really relatively small, like 128, 512 entries. Why is the TLB small? Make it faster. Because remember, what did I say about fully associative? The bigger it is, the more transistors are spread out, things get slow. So they have to make it fast by making it small. However, if it's too small, then we get a lot of thrashing, okay? So TLB is usually fully associative, lookups by virtual address, it returns a physical address. If fully associative is too slow, then you get something called a TLB slice, where you have a first level TLB is direct map, second level is fully associative. Okay. So here's an example from a very old processor, but I wanted to point it out here. Every TLB entry looked like this, where what you see after the virtual address is essentially what's in the page table entry, and the virtual address is a lookup, and you build one of these CAM cells in memory, in transistors, such that you put the virtual address in, it associatively matches, then you get the physical address out, and you get things like, is it dirty, has it been referenced yet, is it valid, etc., is it read-write out of the TLB, and that's what a TLB looks like in some cases. Okay? And the fully associative part is you're matching on this virtual address. So you don't have to look at most of this slide, but I did want to show you, because the R3000 is a simple pipeline, that notice that the TLB is fit halfway in through cycles. So this is your standard instruction fetch, decode, ALU, memory, write-back. Does that ring a bell to anybody, right? 5 stages? Definitely to the 61C TAs, right? So if you look, though, the way that MIPS R3000 pipeline was done was because the instruction is in virtual memory, you got to do a TLB lookup. Well, they did that in a half of a cycle. So the first half cycle is the TLB lookup, and then they did the instruction cache, and then they did the register file lookup in the second half of decode, and then you compute potentially the address, in which case you do the address of a load or store lookup in the second half of the cycle, and then you do the data cache access, etc. So they fit this stupid thing in like half cycles in order to make this thing work, okay? And you can imagine this doesn't generalize very well, okay? So how can we make it faster? Well, notice the way we've described this doesn't have to be that way. Notice we have the CPU gives you a virtual address which goes through the TLB first, then it goes to the cache, and then it goes to memory. Well, notice, for instance, there's part of this translation in the TLB even that isn't translated. Like, look at this offset. See the offset? There's no translation there. So while we're going to the trouble of looking up in the TLB, wouldn't it be nice in parallel to start looking up in the cache as well? Because we've got the offset portion of the address. Okay? So, and this is the main idea here. The offset doesn't change when you do virtual to physical, and so you can use that offset to maybe if the index fully overlaps, you can just start accessing the cache right away. All right, and so in fact, here's a great example. I just wanted to show you. Oops, let's not do that. So notice that we have 4K cache. The index is we have 2 byte or 4 bytes wide. The index is pulled out to look up in the cache, and at the same time, you go into the TLB to get the page number. And then you can compare the page number and the tag, and you do this all in parallel. The only problem is if you increase to 8K, you got to do some tricky stuff, which we're not going to talk about in here. Another thing that you could do, which is a little less popular these days, is you can make your cache have virtual addresses in it. So now you can, in parallel, look up in the TLB and the cache, no matter what the address looks like. We're not going to talk further about that either. But all right. So, putting this all together, we have our virtual address, and we're going to try to get a physical address out of it. And by the way, in the x86, this is after we do the segment lookup. But virtual address, we look up. First portion gives us a pointer to the second portion, so the directory to the second level page table. We look that up. That gives us a physical address, which we put the offset on, and that gives us physical memory. So that's our virtual memory. But this is slow. Obviously, we don't want to do this on every access. So where do we put the TLB in this? The offset sort of gives us an offset in the page. So what we do instead is we take this virtual page ID, pump it through the TLB. We try to do an associative match. If that works, we go directly. We got the physical page right away without any going through any page tables. And then, so that's where the TLB fits. Okay. And what about the cache? Well, so now we got our physical page either by walking through the page table or from the TLB, and now we take this address, and that's the one typically where we pull the index off. The index looks up in the cache. We match the tag, and we have our final block. Okay, so there we go. From virtual address to look up in the actual cache. Questions? Shall we just put it all together for you in one? Yeah. What if you have a cache that's what? Oh, what if it's a cache miss? Well, that's a great question. What typically happens in a cache miss is this load or store, once you've computed the address, is stalled in a spot of the pipeline while the cache miss is serviced, and then when the data comes back, you restart the pipeline and it goes forward. And so in a processor like the one you all have that you're using on your laptops or whatever, this is all done out of order execution, in fact. So while that cache miss is being serviced, the next end instructions are happily going along, and when it comes back, then it goes ahead. All right, good question. Anything else? It seems like this was a heavy lift, right? Pi day or not, you guys see all these pieces. We see the page table, we see the TLB, we see the cache. We've got it all together in one slide. And I think when I click on this, oh, yep. Okay. Let's take a break. So I had a good question during the break, which was, I still don't get what segments are for. That's a great question, because if you think about the slide I showed you, it seems like segments are something on top of all of this. And in fact, think of a segment as an additional level of protection, because I can label my instructions with something like it's the stack segment. Then any stack operations that go outside the segment get flagged with segmentation faults, and therefore I can know that the stack operations had a problem with it, not something to do with paging. And so it is, if you wanted to use them correctly, you could, if you wanted to use them, you could use them as an additional level of protection. It's just that they're not as important anymore as they used to be since we have such big address spaces. So, all right. Now, what happens when we got an instruction that gets looks something up in the virtual address, looks it up in the physical address? This is fine, but what happens if we go to translate and get a page fault instead, and that page fault goes as an exception into the kernel, which runs the page fault handler, which goes to the disk and loads a page from the disk, which then updates the page table entry, and then the scheduler eventually restarts the process. It tries it again, and this time it works. Okay, so that's kind of what we're up against next. And I wanted to just show you this last little exception again. So remember all that stuff about precise exceptions. That's all to make this easy, right? So we take the instruction, tries to look something up. It goes to the page table. The page table entry ends up being invalid. We get a page fault, which goes into the kernel. And at the time when we take this exception, since it's a precise exception, the state is all saved for us, and we can easily restart exactly where we were when we faulted before. That's the key. And now the page fault handler is going to pick something off the disk. It's going to load it to us. It's going to fix up the page table. And now the scheduler will eventually restart our thread back where it was when it page faulted, and we can start exactly at the right place because it was a precise exception, and this time it succeeds. Okay? And so the question, of course, comes into play, which things do we choose to put into our limited memory from the disk? Okay? Because not everything that's in the address space of every process is needed all the time, and that's where paging comes into play, and that's where we're going to come up next. But does everybody see this idea of you get a page fault, you pull the page in off disk, you restore the page table entry, and you restart it? Does that make sense to everybody? Okay, so we're going to assume that we have that technology for us from now on, okay? So now let's take a little bit of a brief right turn. So where are caches in operating systems? Okay, TLBs, cache of PTEs. Page virtual memory, that's memory as a cache for disk, which we just kind of showed you, and you're going to talk more. File systems are going to cache disk blocks in memory. The DNS is caching hostname to IP addresses. Web proxies cache recently accessed pages. How do we know which pages to keep in memory if we're limited? Well, that gets into policy. So that's when we start talking about clock algorithms and other paging algorithms. And we're going to spend a bit more time on the policy. But the interesting thing is there are many, many, many uses of caches in operating systems. And so you should get used to it, right? It's all about, what's the associativity? What do I replace on a miss? How do I keep it coherent or consistent if the underlying thing changes? These are all questions that you should start getting comfortable with because they're going to show up a lot. Okay? Even ARP, I should put this one down. ARP is a translation of Ethernet MAC addresses to IP addresses. There are all of these caches. They're everywhere, okay? So the impact of caches are many. So one is indirect, which is dealing with cache effects. And so this is maintaining the correctness of various caches, the consistency of them, what happens with page tables across context switches, etc. We can start talking about, so that's kind of make sure the caches are even correct. And then, when we process schedule, we might want to do something called affinity. Does anybody remember the word affinity? I used it like lecture 2. So affinity is about association between a place that the thread ran before and where we're going to schedule it now. And you can imagine if a cache has a bunch of state loaded from the thread previously, we would like to reschedule it on the same processor to somehow take advantage of all that time we spent with our cache misses. Okay, and so scheduling starts thinking about things like, if I've got too much demand for memory, which things do I throw out to disk? And then later, if I'm going to restart something, which processor do I want to start it on to get the caching effects to be maximized? Okay? And that's the impact of thread scheduling on cache performance. So knowing that there are caches everywhere is kind of the first step, and then deciding what you're going to do about it, keeping them consistent, scheduling properly, and worrying about performance all come into play afterwards. And then, of course, designing your data structures for cache performance is going to be important if you're actually building a cache. So a great item might be a hash table or a clock, which we'll talk about, or other data structures that you're used to from 61B start becoming very useful to remember when you're worrying about cache architecture. Okay? Now, this is not 152 or 151 or 150 or whichever the numbers are. They keep changing them, and some of them are like 151 is halfway between 50 and 52. That much I know. But in hardware, there's also a data structure question, but that becomes, how do I lay the transistors out to make it fast? In the operating system, we're going to be worrying about how do I lay out my data structures to make the caching fast that the operating system worries about. Similar ideas, different level of technology. So one of the things we're going to address here is we're going to start talking about things like the working set model. So as a program executes, it transitions through a sequence of working sets. So here we have time on the x-axis and addresses. So this is the address space. And if I were to watch an execution, what I would see here is that over time, certain addresses are in use, and then they go out of use while other ones come into play. So that working set model, that cool? You guys want to see it again? Look at that. Ooh, all right. So if I were to look in that little box at any given time and I see which addresses are active, that's my working set. Okay, and if I have many processes in memory and I look at their working sets, and if I add up all the pages in the different working sets and they don't all fit in DRAM at once, then I have a problem because I can't switch between them without loading a bunch of stuff off of disk. Okay? The other thing you can get from this slide, watch it again, is that in any given execution, there are big chunks of the address space that are not in use. Okay, so it's kind of like there's the working set, which is the blue part in current use, and the white part that's not in use is like the anti-working set or whatever, the inverse. That means that during this period of time, these white areas don't actually have to be pages loaded in memory. They can be out on disk. And the process will run perfectly happily because it's mostly not going to page fault because it's only using things in this region. As soon as I go here, suddenly I got a whole bunch of page faults right away because there are blue parts that weren't blue before. But once I get them into memory, then there's no more page faults for a while. So this idea of paging and sort of representing what is the working set of given processes and how can I figure that out in a way to avoid too many page faults is going to be kind of important. And there aren't any magic bullets in this as to what the right thing to do is there, but there's some time-honored ones like LRU. That's pretty time-honored, right? Least recently used. Okay? That one will come up as useful. If I have no other information, that one works pretty well. Okay. Are there any questions on this? Now, I want to point out another reason we're even talking about this. You remember that, the average memory access time formula that we had at the beginning of the lecture where we sort of talked about hit time and miss time? The problem with this, where we view memory as a cache on disk, is the miss time is really expensive. Okay, if I go here and I'm about to start executing in this region and suddenly there's a bunch of pages in the address space that I have to get off of disk, that's going to take a really long time. And the average memory access time during a region there where I'm pulling things off of disk is going to go toward the disk time. Okay, and there's a great rule of thumb that's been true across many generations, which is how many instructions does it take to get something off of the disk? Okay. Seems like it's been about of order 1 million instructions for a long time. Okay, so there's, by the way, I always try to help you guys out with great party facts. That's a great one, right? How many instructions does it, do you lose going out to disk? All right, so that's a good party fact. But what it means is really that I better avoid pulling stuff off of disk as absolutely much as I can, because if I don't, I'm in trouble. Things get really slow really quickly. The average memory access time goes through the roof. Okay? So that's going to be why when we start talking about our paging algorithms, we're going to want to be very careful about which ones we do. Now, what's interesting about this is this working set model is kind of, can be thought of in this way, which is a slightly different way to look at this, which is as the cache size gets bigger, more and more of the working set can fit in memory at once or in cache at once. And as I increase my cache size, what I'm going to see is the hit rate is going to go up, and then it's going to reach some plateaus because, just adding a little more cache doesn't help me any, until I get to a point where I start taking in more of the working set for a little longer, and then the hit rate goes up again. And so as we increase cache size, in general, our hit rate keeps improving. And there's kind of an optimization problem we could think about, which is what size of DRAM, in this particular instance, do I want to give process A, versus process B to try to make sure both of them are running as well as they can? So it's kind of, there's potentially a trade-off between A and B as to how much DRAM they're using. And there could be an optimization where we try to figure out which is the right spot on this curve for A and for B, such that when you sum up all the memory, it doesn't exceed the DRAM you've got, etc. Okay. And we translate, the other thing is as time goes on, and this was pretty clear, I think, from here, as time goes on, you transition from one working set to another. So most programs go through phases that are different. So what was a working set at one point in time is not the working set later. Okay. And we can very quickly hit capacity conflict and compulsory misses. And this is a great way to remember the 3C plus 1 because that's going to come into play. All right. So another interesting model is ZIP, however you want to pronounce that, ZIP, which is an observation that there's a lot of data access patterns which look somewhat like this, which is the probability of access falls off as 1 over like rank to the A or whatever, and the likelihood of accessing the item is 1 over R to the A, where A is a fraction dependent, or is a number dependent on the actual working set application. But what you see here is that's blue here is kind of telling me as I go out to a given rank, I take the popularity, I sort them, I see that as I go out further and further, the popularity has this blue curve, which says as I increase cache size to include some of these less popular items, the cache rate goes up. And what's interesting about this is that it's very rare to access items below the top few, but it's a very heavy-tailed distribution. So a little bit of cache does a huge amount for me, but there's a lot of things that don't fit in cache, and as I increase the cache size a lot more, it sort of tails up. Okay, and so this curve is shown by a lot of things, like website accesses. How many people have run into zip before? Anybody? So this is a good distribution to describe a lot of access patterns. So even a tiny cache gives you a lot of value, but a big cache gives you decreasing value, but still value, and there's a very long tail. So why do I tell you about access patterns? Well, the problem ultimately is we don't really know what the pattern is for any given application. That's up there with solving the halting problem. Okay, and so what we would like to do is we'd like to come up with caching mechanisms for paging that do a pretty good job of adapting to the behavior of the program to give us pretty good performance. And that's what we're going to go for. Unless somebody could tell me that their program behaves exactly like this, where A is, 1.39 and whatever, maybe we could do better. But in many cases, we're going to come up with heuristics that give us pretty good paging. Okay? That's PGP, but not in the way you're used to. So what's demand paging? So demand paging is really this idea that we've been talking about, which is I go along and I make my accesses and they go through the TLB and so on, the page tables, and as soon as I hit a page table entry that's not present or invalid, on demand, right then and there, I go into the operating system, I pull it off of disk, and I clean it up, and then I restart the program. On demand. That's what demand paging means. Okay? And the idea is that most programs don't use all their memory all the time. And so there's actually a 90-10 rule, which you've probably run into in many of your other classes, which is programs spend essentially 90% of their time in 10% of their code. The same is kind of true with a lot of their data. And so it's really wasteful to require all the user's code to be in memory. Now, I will tell you there's another very good reason why a lot of code in a program doesn't need to be in memory. Can anybody tell me other reasons for that, other than the 90-10 rule? Think about libraries. What happens with typical libraries? Yeah. Right. So you have a library full of a zillion functions that get linked into your code, but you're only using a couple of them. They shouldn't. Why bother wasting DRAM space with it, right? It can be out to disk, yeah. So there's a lot of, and modern languages and programming technologies tend to do that, where there's a lot of options you can use, and maybe it gets linked into the binary, but most of the time you're not using it. So that is a reason oftentimes why the active region of memory is a lot smaller than the code total size. So what we're going to do is we're going to use memory as a cache for disk. That's what this demand paging is. So rather than what we talked about earlier, where the DRAM, second level cache, first level cache, etc., is treated together as a caching scheme, now we're going to treat DRAM as a cache on disk. And the difference is those first three levels, or actually today's modern processor, there's 1, 2, and 3 levels on a single chip, and then it goes to DRAM, or sometimes even more levels. What we know is in this set of regions, the caching is handled in hardware. So when you go to access something in the first level cache and it misses, it goes out automatically to the second level cache in hardware, and then it automatically goes out to the DRAM in hardware and brings it back in and cleans up all the tags and everything in hardware. This is actually a software managed cache. So here, main memory is going to be set up with the page tables to look like a cache on a much bigger image that's on the disk. Okay, and that's going to be the operating system is going to have to do that caching. It's going to have to, on demand, figure out that there was a cache miss, pull the data off of the disk, and it's also going to have to do replacement. Remember what replacement means? If I'm going to replace somebody, I've got to figure out which one. Okay, that was back at the beginning of the lecture where we said, well, we could do random or LRU. It turns out when you get to something where a miss is 1 million instructions, then we're going to not want random. We're going to want it much closer to something that's likely to be correct, like LRU. Okay, and so the cost of a miss is going to push us to a more complicated scheme than just randomly choosing something to throw out when I pull something new in. Okay? Questions? Good. So this is the illusion of infinite memory. Now, in 32 bits, used to be that 4 gigabytes was a lot. Okay, 4 gigabytes is now a little, but let's assume for a moment it's a lot. Okay, the illusion of infinite memory is that my illusion is my process has all of memory, and that is illusion is set up by a combination of the TLB and page table, which really says that those things that I've got are either in physical memory or out on disk. And so this illusion is put together by a combination of the paging hardware and my operating system that decides which things are in the page table at which time and which actual pages are in physical memory and which are out on disk. Okay, and that's how we get that illusion. So we give the process the thought that it has all of memory, even when it doesn't. Okay, and the disk is much larger than physical memory. Okay, Seagate. Anybody know what the biggest Seagate 3.5-inch drive is these days? Go for it. What was it? No, I don't think there's a 32 terabyte one yet. There's definitely 10 and 12. They're getting up there. So they're really big. Okay, that's a lot of memory. So you can have a much larger image in disk than you can in memory. And so the idea is that this is a transparent level of indirection, which is the page table, supports flexible placement of the data, and variable location is transparent to the program. So basically, we are going to transparently fool the process into thinking it's got a lot more physical memory than it does by deciding how we manage that page table. Okay? And this is transparent, which means the process is going to access some missing page. We're going to trap into the kernel. The kernel is going to clean it up. We're going to go back up into the user program, and it's going to continue as if nothing happened. And the only way it would know the difference is if it were somehow managing time and watching. Okay? Because it's just going to pull it off of the disk. Okay? Good. So that's where we're going to go next time. So demand paging is caching. And so we can ask questions like, what's the block size of this cache? 1 page. What's the organization of this cache? It's fully associative. We talked about this last time. Why? Because there's arbitrary virtual to physical mappings are possible. We can put any physical page into any spot in the virtual memory. How do we find a page in the cache? First we check the TLB, then we do page table traversal. What's the page replacement policy? LRU, random. We're going to do something that approximates LRU, for instance, with the clock algorithm. What happens on a miss? We go to the lower level to fill the miss off the disk. What happens on a write? Do we do write through or write back? Write through or write back? Write back. Definitely not write through, right? That would mean that every store is 1 million instructions worth of time. Okay. All right. So in conclusion, we remembered last time the principle of locality. We've been using a lot today. We reminded you of compulsory conflict capacity and coherence misses. We talked about a bunch of cache organizations. This summary page is 61C. Make sure that this makes a lot of sense to you. Okay, that's review. We talked a lot today about the TLB, which is a small number of page table entries and optional process IDs are stored in this TLB. It's fully associative. On a miss, the page table is traversed. And if there's an invalid PTE, we get a page fault. We talked about precise exceptions. All previous is a well-defined exception place where all previous instructions have completed and that one and nothing else is completed or started. And we can manage caches in hardware or software or both. And next time, we are going to manage our page cache in software. So you guys have a great weekend. Happy Pi Day. You should all go out and celebrate by reciting a few digits to everybody.